In this video, we're going to be defining an antiderivative and then finding some indefinite integrals. So first, let's talk about what an antiderivative is. An antiderivative is the inverse of a derivative. It undoes a derivative, or it works backwards from deriving. So if I have a function that's a derivative function called f, lowercase f, the antiderivative notation is a capital F, and that symbolizes the antiderivative of that derivative function. So for example, if I take the derivative of an antiderivative, they undo each other. I'm left with my original function. We could do it in this notation, or we can do it in this notation. Either way, an antiderivative is the inverse of a derivative. They undo each other. Let's investigate that just a little bit further here. Let's take three examples of a function, and we'll find the derivative of each of these functions. The derivative of x squared is 2x. Going over to this function, if we find the derivative of this function, we get the same thing. The derivative is 2x. So different function, same derivative function. Same thing with part C here, this function x squared plus pi, its derivative is also 2x. So as you can see, the derivative is the same even though we have three different functions. So what is their relationship? What do they all have in common? Well, they are all involving a constant. Either it's a 0, or it's a integer, or sometimes we have some symbols like e or pi representing an irrational number, but it's still just a constant number. And so when we take the derivative of that, we get 0. So we're just deriving that function with a variable, and we get the same derivative regardless. So an antiderivative is asking this question. So 2x is the derivative of what function? So let's try and work backwards now. Well, as we can see, the answer to that question has many possibilities. There are many possible antiderivatives to 2x, any of these plus many more. So what we do is we add this variable called c. It's called the constant of integration. It represents any constant number. And then therefore we can write this, and it represents the family of all possible antiderivatives. And when we add in that constant of integration, we now have what's called an indefinite integral, or a general solution. So let's take a look at some more notation that we're going to have to be familiar with. So that capital F of x is the antiderivative. If I add my constant of integration to my antiderivative, it represents my indefinite integral. And here's another way to represent the indefinite integral using a symbol called an integrand. So there's our integrand of this function, and here is with respect to the variable being used in the function. It's called the variable of integration. We could do it in that notation, and then we can see that if we take the derivative of the indefinite integral, they undo each other, they're inverses of each other, and we get that original function left over. So one more way to think about it is if we're deriving, we're moving in this direction. The derivative of f is f prime, the derivative of that is f double prime, and we could keep going in that direction. If I want to work backwards and undo my derivatives, I use an integrand. So the indefinite integral of f double prime is just f prime, and then if I integrate that, I get back to my original function. So derivatives work one way, integrals work the opposite direction. There is one main rule for integrating. It's called the power rule of integration. And it's basically the opposite of the power rule, not the opposite, the inverse of the power rule for deriving. So if I take a function that's raised to a given power and I want to find the indefinite integral, I'm just going to add 1 to the power and then set the denominator equal to that new exponential value. And when we do that, we can never have 0 on the bottom of a fraction, so that value can never be -1. And we'll talk about ways that we can deal with it if it happens to be -1 in the future. But first, let's just practice using the power rule of integration. Let's get used to this. So the first the first integral property is an integral of a constant. So there's an implied 1 here. You can put any number here. The antiderivative of a constant is just the variable that we're being used. So check out that variable for integration there. And that's the variable you're going to plug in after you integrate. So if I take a variable raised to the 0 power, that's always 1. But if I add 1 and use my power rule of integration, we can get the integral. So 0 plus 1 is x to the first power. And on the bottom, I'm going to use my new exponential value, which is 1. And so x to the first power divided by 1 is just x. And then whenever we find an an indefinite integral, we're always going to add that constant of integration. In the future, we'll actually be able to solve for that value. But for now, it's just a generic c representing any constant value. All right, let's try and integrate 3x. Let's find the indefinite integral. So we're going to take that constant value that's attached to a function variable, and just like the constant rule for derivatives, we're just going to shift it out front and focus on the variable. So if I integrate that variable, it's x to the first power. I'm going to add 1 to the exponent and divide by the new exponent. So I have x squared over 2. And we can plug that 3 and distribute it back in. And so we have 3 halves x squared plus c. You can always check your integration or your indefinite integrals by deriving. So if I go back to my first one, if I derive x, I just get 1. If I derive 3 halves x squared, then I'm taking that 2 down to the bottom and multiplying. I'm left with 3, and I subtract 1, so I'm just left with 3x, which is what I started with. So you can always check your integration by deriving and make sure that you're getting equivalent values. All right. Another thing that we want to practice doing is rewriting before we integrate. So if you ever have a variable on the bottom of a fraction, we can rewrite that using a negative exponent, and then we can use our power rule to integrate. So if I add 1 to that exponent, I get x to the negative 2. And if I divide by that new exponent, I have negative 2 on the bottom. We're going to say plus c, adding in that constant of integration, and we could rewrite it. We could leave it in that form or rewrite it, just shift that negative 1/2 out to the front. We could also rewrite it as negative 1 over 2x squared and put that x squared down at the denominator position. Either way. Let's do another practice. Again, rewriting. So rather than a radical, we're going to use a fractional exponent. So the square root of x is x to the 1/2 power. We can now use our power rule for integration, add 1 to the exponent. So 1/2 plus 2 halves is x to the 3 halves, and divide by the new exponent. And then we could rewrite it. So if I'm dividing by 3 halves, I'm really multiplying by 2/3 and add in that constant of integration. Last thing, there are trig identities that you just kind of have to memorize or just think backwards from your derivatives. So you can take a look at a list of identities and work on memorizing these identities. So the integral of sine is negative cosine. And again, we're going to shift that constant out to the front. Then we can multiply it or distribute it back in after we integrate. So we're left with negative 2 times the cosine of x plus c. And if you think backwards, the derivative of cosine is negative sine. And negative sine times negative 2 would be positive 2 sine x. So there's the power rule of integration and the definition of antiderivatives and indefinite integrals.